what's up? I'm here with Misty today in front of the beautiful Azusa Hookah Lounge out here in Las Vegas. And tell us a bit about yourself, Misty.
Well, I am in school for law enforcement. I want to be SWAT when I am older. So that's my main goal.
She's super scary. I could see her crashing through my window.
Yeah, so I'm just busting and be like, surprise!
I mean, I'd be scared of a girl with like 18 tattoos.
18 tattoos, yeah. Pretty much. Which one are you interested in?
What's your favorite tattoo?
I think this one. The cover up, not done. It's going up.
It's going up.
It's going all the way up.
So I have a lot of science friends who regret the tattoos they got. They got like nerdy science equations like scrawled over their body.
Well, it's probably because once they get it, they see it and they're like, oh, you know what, I didn't want this equation all over my body. You know, you gotta get something that's meaningful to you. Even though you're a scientist, you probably don't want some equation that you do every day on you.
I'm talking to you, Jonathan, right now. You know you're talking about Einstein equation right here. So in pre-production, you were talking about how you love black holes.
Yeah, big ones.
Big black holes.
Yeah.
What's your favorite black hole?
Well, you were talking about M18.
M87.
M87, there we go.
Okay, so I'm curious, do you read popular science books?
No. But I was in school and what interested me was one of my science teachers. She was talking about how one of the black holes was so enormous that it can actually like pull objects in from like outer space. Like things were actually like entering the black hole.
Yeah, so black holes kind of come in like two classes.
Okay.
So there's stellar mass black holes, so a black hole that weighs about as much as the sun.
Jesus.
And then there's what they call supermassive black holes, which these are the black holes at the center of galaxies, and they weigh like 1 billion times as much as the sun.
Okay.
And so no one really knows how those form, the ones that are at the center of galaxies. And so, but they both have this property that once you're past a certain point called the event horizon, you basically can't exit the black hole anymore. So they both have this property, but how big the physical extent of that region is, so the event horizon, is going to be bigger for the more massive black holes.
Okay. And how do these black holes start? The other ones, the ones that can actually.
So the stellar mass black holes.
Yes.
So the basic idea is, so first of all, we have to understand how stars work. Okay. So what is a star?
You tell me, scientist.
Okay, so imagine a star is just a big ball of hydrogen gas. Okay, and so let's think about what's going on in the star. Okay, so gravity is pulling all the gas in the star inwards. Okay, so now what prevents the star, all that material, from just collapsing to a point?
So it's collapsing?
So it would collapse, but we see that it's not collapsing.
Yeah.
Right? So there must be some force that's pushing it,
outward.
the gas outwards, to balance it out. So what is that force? Any idea?
Gravity?
So gravity's pushing it in.
Okay.
Gravity's pushing everything in, and so there's actually pressure.
On the inside?
The pressure of the gas that's pushing it outwards to counteract gravity. Okay. So that pressure is coming about because there's a nuclear reaction going on in the sun. So basically all the hydrogen gas is combining together to make helium. Okay? And when that process happens, energy is released and there's pressure that can balance out the inwards gravitational force. Okay? So that happens when the hydrogen is being converted to helium. And so if you think back to like your 3rd grade chemistry class. Okay, you remember the periodic table?
Of the gases?
Of all the elements. Yeah. So hydrogen's the lightest element, and then next is helium, and then you keep on going up, and there's heavier and heavier elements. So what's happening in a star, or like the sun, is those elements are combining together through nuclear fusion. Okay, and so the hydrogen is going to turn into helium, and then the helium is going to turn into like carbon and oxygen and heavier elements. And so when you take two light elements and combine them together, it releases energy. Okay, but at one point when the atoms get bigger and bigger, they lose that property. It's actually the opposite. So if you have a big atom and you combine it with another atom and then it gets even bigger, it actually costs energy instead of energy being released.
Okay.
When you have big atoms and you break them up, that releases energy.
Okay.
When you have little atoms and you combine them together, that releases energy.
Okay.
So in the sun, you start out with little atoms, you combine them together to make bigger and bigger ones. It keeps on releasing energy until you reach iron.
Okay.
Okay, and then once you reach iron, then you start not gaining energy, or you stop releasing energy when you combine the atoms together.
Okay.
And so now there's no more pressure in the star anymore. Gravity is pushing things in, but there's no pressure outwards to balance it out.
Okay.
And so basically gravity just is going to collapse the star down into basically like a point. And that's basically how a black hole is going to form. So there's actually like intermediate stages where you'll go from like a normal star to a neutron star to a black hole, provided that the star is massive enough.
Okay. So it'd have to be a pretty big star.
It would have to be a pretty big star. So probably like our sun is probably not massive enough. But if you have a more massive star, this weighs, I don't know, 8 solar masses, then you might be able to produce a black hole.
Okay.
But the point is, how much is that black hole going to weigh approximately?
A lot, depending on how big it is, if it's a stellar or a super massive
Right, so we're starting with roughly a stellar mass. So it's like, we're starting with like, oh, it weighs like 1 times the sun, or 8 times, or somewhere around that ballpark.
Yeah.
So when we collapse everything to a point, you'll have approximately the same amount of matter left. So the black hole is probably going to weigh about a stellar mass, or tens of stellar masses.
Okay, makes sense.
So this mechanism can explain black holes that weigh like stellar mass, but not the supermassive black holes.
Supermassive, or they're just unexplained?
They're unexplained, exactly. So it's like, you can try and estimate. You can say, okay, we'll say I produce like a stellar mass black hole.
Okay.
And you can imagine, well, what about if it eats up a whole bunch of matter?
Is that maybe how it got so big?
Maybe.
Maybe.
But think about how much matter it would actually have to eat up. Yeah, so basically, imagine you start with a black hole that's like weighs as much as the sun.
Yeah.
Like if you want to get up to 1 billion times more heavy, you'd have to eat up like 1 billion other black holes.
Okay.
That's like a shit ton of black holes.
Yeah, it's a lot.
So just to throw out that book recommendation again, it's called The Case for Mars by Robert Zubrin, link below. I thought it was super inspiring. I can't even believe I hadn't heard of this book, even though it's like 15 years old. So Misty, thanks for hanging out.
Of course.
And
thank you for having me and coming along and nerding out, you know. And I hope I see you again. And we get to nerd out.
Vegas is a small place.
Yeah. We can have fun next time.